All right, welcome to the fourth and final snow day lecture for February 19th. And we're going to talk now about the third type of reaction types that we're going to be studying, and that is oxidation reduction reactions, are often called redox reactions. And you're going to be able to identify those reactions, perhaps to predict products, and also talk about what is an oxidizing or reducing agent, because those are words people want you to know. So redox reactions are ubiquitous. They're probably, in one manner of thinking, almost every type of chemical reaction is a redox reaction. So I will give you a common example, and that is iron and steel corrosion. The actual process is actually kind of complicated, given this is something that happens all the time, but you can boil it down with this, that iron metal reacts with oxygen. Water helps a little bit. The main product is iron 3 oxide, Fe2O3, and some other stuff. The other stuff depending on the exact conditions, whether that's pure water, whether it's salty water, and stuff like that. Now, these are among some of the oldest reactions studied because people had found that almost every other element reacts in some way, shape, or form with oxygen. So that's why these are often called oxidation reactions, or part of it is anyway. Okay. So let's look at this. You will note that, so let's focus in on the iron and the oxygen. These are both neutral compounds. This is just iron metal. This is oxygen gas. And in the product side, we've got Fe2O3. So that formula should hopefully be able to tell you that iron is a +3 cation and oxygen is a -2 anion. So what happened here? Something went from neutral to being a positive ion or a negative ion. Think about what subatomic particle would affect that cause. And so the iron, in going from something that is neutral to a +3, must have lost electrons. And we say that process is oxidation. So anything that is oxidized has lost electrons in some way, shape, or form. The oxygen went from being part of a neutral compound to a -2 anion. So, and you reduce in charge by gaining electrons. Now remember, electrons are the only subatomic particles that could have done this because, well, neutrons don't have charge. And if you were to swap protons, you're actually changing the element, which we're not doing here. So that leaves electrons. And we say that things that gain electrons have been reduced. So redox reactions are at their heart electron transfer reaction. And the other thing to note is, because electrons are matter, they must be conserved. So if something loses electrons, something else has to gain those electrons because their number has to be conserved. So oxidation and reduction processes always occur together, hence the name redox reaction, because they always have to be the same thing. So to summarize, oxidation is losing electrons, reduction is gaining electrons. There are a couple of these, but this is one of the more prominent mnemonics to remember which is which: oil rig. And the only thing that you have to remember out of the mnemonic is the fact that you're talking about electrons right here. There's a Leo the lion goes grr, but I think that one is pretty lame. Now, here is the meat of this lesson. Determining what was reduced and what was oxidized is trivial when the species involved actually change charges. But that's not always the case. So what you're looking at here is one of the most commonly performed redox reactions ever, and that is simply the combustion of natural gas, which, for example, my furnace is doing right now. What's oxidized? What's reduced? Can you tell? And everything here is neutral. nothing has an explicit charge, so it is not obvious what element gets oxidized, what element gets reduced. So let's make it obvious. And so we're going to introduce a concept, something that is called oxidation numbers. This is sort of a fake charge. It is an artificial construct, but it is useful in tracking electrons to kind of see what gave up electrons and what took them. And unfortunately, you just have to remember a couple of rules. So I'm going to go through these rules. I would encourage you to write them down as I say them, just to help you commit them to memory. So first of all, in free elements, so either the elements by themselves like helium, manganese, or in compounds made up of an element, the oxidation number is always 0. So things like H2, S8, O2, it's always going to be 0. All right, next rules. So if you're looking at actual straight up ionic compounds, since the anion and the cation don't exchange electrons, you want to treat them separately if that is the case. All right, now the nitty-gritty. For monoatomic ions, so things like sodium or chloride ions, the oxidation number is straight up equal to the actual charge. If you see oxygen in a compound, it's probably going to be -2. So if it's O2, the gas, it's 0. Anything else that's going to be -2, with this one minor exception that we don't actually see very much, the peroxide anion. Hydrogen, when it's in a compound, is usually +1. Now remember, H2 is 0. And there's another weird case where if you see it combined with a metal like NaH, then it's a -1 ion. But other than that, it's almost always going to be +1. All right, next set of rules here. Fluorine, when it's combined with any other element, it's going to have an oxidation number of -1. That's it. So it's either 0 in F2 or -1 everywhere else. If you have a neutral molecule, the sum of all the oxidation numbers has to be 0. If you're talking about a polyatomic ion, something like sulfate, then the oxidation numbers have to add up to the overall actual charge on the ion. And so basically the idea is that there are a couple of elements like hydrogen, oxygen, and fluorine that consistently have the same oxidation number. And using that and this last rule right here that talks about what oxidation numbers add up to, you can figure out the oxidation number of another element. And the thing is that a lot of other elements can be flexible in their oxidation numbers. So I'm going to give you a couple of quick examples in increasing complexity. So the first one is the ammonia molecule. So the idea is that we want to assign this oxidation number to every single atom in here. Now, so look for the ones that you know. So look for hydrogen, oxygen, or fluorine. So this is hydrogen in a molecule. It's not bonded to a metallic element, so it's going to have an oxidation number of +1. And this is via rule 5. Now there's 3 of them, so they add up to a total of +3. Now NH3 ammonia is a neutral molecule. So that tells us that the nitrogen has to be negative, and specifically via rule 7, it has to be -3 because that is the charge that will add up to 0. So we have a total of +3 from each of the hydrogens, and an oxidation number of -3 makes them all add up to 0. So in this case, we would say that this is hydrogen in a +1 oxidation state and nitrogen in a -3 oxidation state. Remember, these are not charges for real, but we're sort of pretending that they are. It's almost like these oxidation numbers are almost like pretending that everything is an ionic compound. That's one way to think about it. So let me give you a more complicated example in this case. And this is the perchlorate ion. Now remember, perchlorate, always soluble. So what are the oxidation numbers of the oxygen and the chlorines in here? So look for the ones that you know. Oxygen, it's part of the compound. It's not the peroxide, so these are all going to be -2 in this case. So now what I want you to do is think about, and pause if you want, what is the oxidation number on the chlorine in here? All right, so -2 each via rule 3. We have 4 of them, so that gives us a total of -8. Now this means that the chlorine has to be positive, but remember that the rule is that they have to add up to the overall charge, whether that's 0 or something else. And because this is a -1 ion, so all of the oxidation numbers have to add up to -1. And so -8 and +7 add up to that overall -1. So be mindful of that. All right, so that's kind of some examples as to how to determine oxidation numbers. Now, with that under your belt, let's look at the problematic reaction that I proposed at the beginning of this video, or in the middle actually, the combustion of natural gas, of methane. That would be the CH4. So what you want to do is, now that you can do this, go through and assign all of the oxidation numbers for all of the elements in this reaction. And first I want to balance it, so make sure it's balanced. So 2 waters. Everything else should be good. All right, so, and 2 oxygens, sorry. So pick the, now I'm just going to go from this one here. So hydrogen, part of a compound, +1. And that means that carbon has to be -4. And let me show you the trick that I used when I was trying to figure this stuff out. I would write the oxidation number of per atom on top. And at the bottom, I would write the total for that element. So I've got +4 coming in from the hydrogens. It's a neutral compound, so that means you have to have a -4. And being that there's only one carbon atom to distribute, that's -4 per carbon. All right, now the really low-hanging fruit, oxygen, the element by itself is always 0. So let's do the carbon dioxide. So that is -2. There's 2 of them. So we've got -4. That also tells us that there has to be a +4. There is only one carbon to distribute that. So those carbons are +4. And if you do the water, let's do my example here. So oxygen is -2, so which means you have to have a total charge of +2, which means that these hydrogens are +1 each, which is consistent with the fact that, yes, oxygen is usually -2, and hydrogen is usually +1 when they are part of a compound. Now that we've done that, we can actually see where the electrons went. Remember, the whole name of this game was electron transfer. That's +1. So what you want to look for is a change in oxidation numbers. So the carbon in methane had an oxidation number of -4. It has an oxidation number of +4 in the carbon dioxide. And we're going to say that that kind of tells us that that carbon atom actually, or that molecule, gave up possibly 8 electrons. That's not quite right, but getting there. And that the oxygen went from being 0 to +2, but there are 2 of them there. But also don't forget that the oxygen went into two places. So it's also there, and it's also in the carbon dioxide as well. So the carbon went from having a -4 to +4 oxidation state. The oxygen went from 0 to +2. And actually, if you look at the coefficients, do the balancing, you actually find out that overall, the oxygen atoms, so going from 0 to -2 implies you're taking in 2 electrons, right? Except that there's actually a total of 4 oxygen atoms. So that actually adds up to the 8 electrons that were given up by the carbon. So that actually matches. So the moral of the story, the oxidation number of the element carbon increased. So we say that it was oxidized. The oxidation number of the element oxygen went down. We say it was reduced. And just so you have to remember more things, note that whatever is oxidized, the substance that is oxidized, in this case the methane, is also the reducing agent. The substance that was reduced, the O2, was also referred to as the oxidizing agent. So the way this seems counterintuitive. The way to think about it is that whatever is, the thing that is oxidized makes the reduction possible. And likewise, the thing that is reduced by virtue of accepting the electrons makes the oxidation possible. The other thing I will point out is be careful if someone is asking you a question such as what is oxidized or what is reduced. Be very careful to answer to see if you're being asked if the element or if the species is being oxidized. So for example, in this case, the element carbon is oxidized, but if you were asked about what the species that is oxidized, you would want to say the full compound that it's in, methane. Likewise, the element oxygen is reduced. The species that is reduced is O2. So be mindful of that. And one more thing. So I'm going to go to a different one to give you one last little tidbit of these. So here is a easy to decode ionic equation. We've got copper metal reacting with silver ions to react with copper ions and make silver metal. So, and it is common to break up once you identify what's oxidized, what's reduced. So let's go through and do that. Well, I've got your attention here. Get the pen up. So let's go through what the oxidation numbers are. So copper by itself, 0. Same thing for silver. Everything else is an ion. So the oxidation number of silver and silver plus 1 is +1, and it is +2. And if you want to make all this work, remember that we need coefficients of 2 in front of there to make this work. Now, so the element and the species copper is what is being oxidized, and is being oxidized to the species copper +2. And if you wanted to look at that in isolation, you'd say that copper becomes copper +2 and 2 electrons. So you give up 2 electrons to become that. Now this process represents the specific oxidation process, and as such is referred to as the oxidation half reaction. Now you could do the same thing for the reduction process. Silver goes from +1 to 0. So you could say that silver +1 plus electrons would give you silver metal. This equation specifically talks about the reduction process, and as such is referred to as the reduction half reaction. Now here's a little clue. This is going to help you in a later chapter balance very challenging equations. Now I kind of said here that this didn't work out because the charge didn't balance. You've got silver +1, and so you end up needing 2 silvers. Now you would have known that by splitting these up into half reactions, because the copper reaction, the oxidation reaction, produces 2 electrons. Each time the silver reduction reaction occurs, it only needs 1 electron. Now the electrons have to be conserved. So for every time that the oxidation reaction occurs in this example, the reduction reaction must occur twice to take up the 2 electrons. And so this would tell us that we'd have to put coefficient. So if I do that and just distribute that and put a coefficient of 2 in front of everything here, and we recombine them, the electrons cancel, and we would get copper plus 2 silvers gives you the copper ion plus the 2 silver metals, and now giving you an equation that is both balanced in atom and in charge. So keep that in mind, and we will see you on Thursday.